Can you see my slides?
Yes.
Okay, so first I'm gonna go through some background about integrating AI in simulations, and then Romit will go through our example. So since this is a new topic for us, that's why I have some background and motivation for why you would care about coupling AI and simulation. Okay, so one use case is active learning. If you're not familiar with that term, you might have called it experiment design. So you might want to use machine learning to decide which simulations to launch. Maybe you want diverse simulations, or you want to pick the simulations that will improve your machine learning model. Or maybe you're trying to predict something really specific, like you want to predict a certain property of molecules, then that could influence which simulations or computations are most important to run. And then also, let's say you have a machine learning model that's pretty good, but it's getting worse over time, then you might want to use active learning to collect more data. So maybe you're initially satisfied with your machine learning model, you're using it at scale, but maybe you're monitoring its error. And then you say, if it is below some threshold, launch some more simulations to get more training data. And an Argonne example is this paper by Ganesh Subramanian et al. And again, this is all in the markdowns, so you can click the links there. If you want to see an example code using active learning. Something that Romit and I have been working on is surrogate modeling. So let's say you have an expensive simulation, and you could, let's do an automatic timing. Just a second, gotta uncheck that box. Okay, sorry, you can see my slide again, right?
Yeah.
Okay. Okay, so you could have a machine learning model that replaces your whole simulation, but since today we're talking about coupling AI and simulations, this would be the context where maybe you only replaced part of your simulation with machine learning. And so the output of your machine learning model needs to go back into the simulation. And one example we're involved in with collaborators is a simulation for an automotive engine, and we're replacing just an expensive part with the machine learning model, and the output of the machine learning model needs to go into the rest of the simulation. And so we would want to directly couple the trained ML model with the simulation. And then alternatively, you could be replacing some inaccurate part with a machine learning model. And an example that Romit and I have worked on, a different example, you can find at this TensorFlow foam repo, where we're able to skip solving a PDE because we plugged in a machine learning model, and it feeds back into OpenFOAM, which is a CFD solver, to solve the remaining PDEs. And in this code, Romit was able to couple OpenFOAM, which is a C++ solver, with TensorFlow by using the TensorFlow C API. So we don't go into Python here. Romit, do you want to comment anything else before I go on?
No, that sounds good. So just to remark, the reason we are showing you this and why we are working in this area is basically motivated by physics-informed machine learning. So we try to bridge the gap between traditionalists, there may be some of you in the audience, and people who are well versed with machine learning techniques, and so a lot of the legacy codes that are out there, like OpenFOAM, for example, or some of these climate models, have been developed in Fortran or C++ or C over many decades. So to completely replace all of them by something in Python is probably not the best way going forward. So this research tries to bring those two ecosystems together. And in this article, we use the TensorFlow C API, but I don't know if Bethany will talk about that, but we are right now working on using the mini app actually that we will demonstrate today to work on a more general class of bindings between C++ and Python, where you can do arbitrary tasks in Python and then go back to C++ for your legacy compute.
Mm-hmm.
Yeah.
Yeah, so although today we're walking through directly coupling with Python, if you want to see an example coupling with the TensorFlow C API, you could look at this repo and maybe take advantage of Romit being around today to ask questions. I'm volunteering you, Romit. Another reason you might want to couple machine learning and simulation is to reduce I/O. So a lot of people have a big I/O bottleneck. And so you could have a machine learning model that compresses your simulation results. So you could think of something like along the lines of PCA or an autoencoder. And so right after the simulation, you apply the machine learning model, compress the results, and then what you save to disk is the compressed version. Another case would be that you want to train machine learning model on your simulation, but you don't want to save to disk in the meantime because that's a big I/O bottleneck. So you want to train online, go feed the simulation data directly into your machine learning model. And another reason that you might want to do this immediately before saving to disk is that maybe you want to do some analysis on the simulations to see how they're going, see if it's working, if you need to adjust anything. And here's an Aron example, doing in situ compression. An alternative use case would be that you want to control your simulation with machine learning. For example, maybe you have some simulation parameters that the machine learning model could be tuning, or you want the machine learning to decide which numerical scheme to use. And another example that Romit has worked on is using reinforcement learning for this. And so here I linked to another one of Romit's repos. Romit, do you want to say anything else about this?
No, I mean, so what we are talking about today is basically can do general purpose data-driven tasks. So, this is a specific example of one of those reinforcement learning, in situ compression, sort of regression type models, in situ regression type models. They all fall under the same umbrella. So yeah, they're all aligned with each other.
Okay, and other reasons you might want to couple simulation and machine learning, you may want to be doing some kind of data assimilation to augment your simulation. You might want to, maybe your simulation is imperfect in known ways and you have a machine learning model to model the discrepancy or closure. And sometimes machine learning models have a solver embedded in the loss function. Okay, so broadly, there are different ways to couple AI and simulation. And these next few slides are vocabulary from this paper, a terminology for in-situ visualization and analysis systems. So one way to characterize how you're doing this is the proximity of the coupling. So you could have the ML and the simulation on the same node, or they could be different nodes but the same computing resource, so like 2 theta nodes, or you could be coupling 2 distinct resources like Cerebrus and theta. And then another way to describe your coupling is how the data access works. So direct access would be that the two are sharing the same memory, and may or may not need to copy data. Indirect data access would be they each have their own logical memory, but either way you need to think about synchronization. And then there's also how you're dividing the execution. So you could think about dividing over space, so you have different resources. So then you need to think about how much you're allocating to each part of the problem. So how much of the compute resource is for machine learning and how much is for simulation. And this is a problem in and of itself to decide how to balance that and keep them both utilized and transfer the data back and forth as necessary. And then the example that we're going to go through today is time division. So we're using the same node for both the ML and the simulation, but we're switching between them in time. And then you might not need to transfer your data, but you're blocking each other. So we can't, in the example today, we're able to have the machine learning and simulation access the same memory. So we're not doing all this data copy, but we can't run them both at the same time. And to give you an idea of some ways this can fit together, here's a figure that adapted from a figure that Venkat made, again, based on that paper. So one example is you have the simulation and AI on the same compute resource, and you could call this loosely coupled. They're different processes sharing space. Tightly coupled would be like what we're doing today, where the AI is called from the simulation and we're alternating in time. And then you could have the simulation and AI on totally different nodes, and then you need to move the data, but you could be executing them both at the same time. Okay, so does anyone have questions on that before Romit goes through the example?
I guess not.
All right, Romit, you can take it away.
Okay, great. Okay, so I'm going to share my screen. Okay, so I'm hoping you can see my screen now. I'll take that as a yes. Okay, yes. So so I'm going to be doing this the way, so going through the example just like I was an attendee. So I will be cloning, I will be compiling, I will be, I'm doing everything just the way that you would. So if you run into any trouble, hopefully I should as well. But before we do that, I'd like to go through some of the code because it's a little tricky. When we were compiling a bunch of this code, we didn't find a lot of documentation online. So with the folks here at LCF and elsewhere, it was a little bit of a trial and error process to come up with this mini app, but we're happy with the way it is right now. So we are hoping that you find this helpful. In comparison to maybe a few other talks you listened to yesterday and the day before, we'll be looking at C++ code. So depending on who you are, you might be celebrating now or cursing him. But hopefully you find it interesting. And once we go through some of the code, and we can go and start coding in the terminal. and hopefully get you started with your first ML and simulation coupling happening at the same time. Okay, so the code, fortunately, translates over from KNL to GPU, so we can use the code, look at it, and the only difference is how we then run it on both these systems. So you can follow me by going to the GitHub repository for our hands-on. I'd highly recommend that you keep a browser open if you have another monitor with the instructions and then type in the terminal. So that'll be easy, right? So the way these examples are set up is that we are calling Python from C++. That's the high level one sentence explanation, right? So we are calling Python from C++. In order to make that happen, we need to hit a couple of capabilities. We need to have a couple of capabilities. One is to initialize a Python shell from C++, and the second, or Python interpreter from C++. And the second thing is to exchange data with it, right? So if we can handle both of these two things, then we can send data to Python. Python can run some compute on it, send it back to us. So C++ can take a portion of its compute and send it to Python, which it can do easily. Writing Python code is way easier than C++, right? So that's kind of what motivated our work over here. So if you go into, for example, the theta KNL directory, you will see that it looks like this, right? And we will be using CMake, right, to actually build our mini app, our example. And when we build it, we will have to compile with the right libraries, and we'll go into these libraries. For example, are Python specific or say TensorFlow specific, and we will figure that out. So let's dive into the C++ file over here. If anybody needs me to make the font larger, maybe this will help. Okay.
Yes,
so
better.
Sorry.
Yeah, that's better. Thank you.
Sure. Yeah. So the example today is something that if anybody's taken a intro level course to numerical PDEs will be very familiar with. So it's basically the problem of a Burger's equation solution. So you have a PD given by the Burger's equations. That's du by dt plus u du by dx equals viscosity times d to u by dx2. So very simple. What we want to do is we want to simulate this this equation, the system of ODEs exactly, right? So, and when we simulate this, we also want to record some of this data for a machine learning task. Okay, the idea will be to make to send snapshots of the solution of a PD, send it to say, a Python module that records them and then does some operations on them to learn it could be a surrogate model, to learn a compression. In this case, we are going to try and build a surrogate model. Okay, and there are details related to this method that are there in the repository. There's a paper that it links to where you have more detail. But high level, we have a solution. We want to send data to Python. Python will do something on it, go back to the solution. Okay. So over here, if you look at this this file, the starting point is, it's C++. So we want to have a main function. We want to declare some functions which we will be using within our main function and within our loops, right? So the syntax here is key. A lot of this is adapted from the Python C API. So Python provides a API that lets you talk to C in either direction. So you can be in Python and call a C function, or you can be in C, call a Python module. And so, for example, what you want to use is over here. So these three lines that you see over here, py initialize, and these two lines over here are basically starting a Python interpreter. So if you, I'm sure you've opened up the terminal in your Linux or your Mac machine or Windows, if anybody's using Windows, and you've typed or you've hit Python in it, right? And it starts up a shell kind of. So you can use that if you want for some simple calculations. but essentially this is what it's doing from C++. So it's initializing a shell and keeping it on standby for the entire simulation, okay? All right, so these next two lines over here, they are actually importing a Python library, sys, so, and then appending the current path, so adding the current working directory to the path. So py run simple string is essentially as if you were typing this into the Python interpreter yourself. Oh, by the way, at any time, if you're confused or, you know, for whatever reason, please stop me and ask questions. I'll try to answer. Okay. So, so that is the purpose of these three lines. So this is kind of like, you can construct a hello world sort of example from this. So you have a C function and you just initialize the Python and you say print hello world and then you exit. So that can be an interesting first example to try on your end, right? But we're going to go a little further. So in order to exchange data from Python and C or C++, we need to use something a little more efficient to send data. So the Python C API does allow you to, for example, send tuples of items from C to Python, so lists. But that's not very efficient. So we need to use the numpy C API. So if people have been using Python previously, I'm sure you know about numpy. It's like a linear algebra package, but numpy also provides a C API that lets you call numpy from C. So you can actually use numpy from C directly without even going to Python. But we do want to use Python because we want the flexibility and the ease of use of, you know, actually typing, like coding up our functions in Python. So we want to use the numpy C API, but only for exchanging data. And you'll get example, and you'll see downstairs how exactly that's happening. And the numpy array is initialized using this particular function call, okay? So again, this is nothing special. This is all available in documentation online. It's a lot of documentation. And it's a little difficult to parse. So we've been working on this for a few months to get the most essential bits into one application, okay? And you can see I have some helpful standard output statements over here so that when we run our example, you'll see that it's crossed these lines, okay? All right, so now the Python C API relies on constructing these pointers to Py objects, which actually hold information related to the Python code that you want to call. Okay, so over here, we will load a module or basically a .py file from the C++ code called Python module. So just to show you what I'm talking about, if you go into you know, at the end of the day, when you build this C++ application, you get this app executable. Within the same directory, you need to have a Python module.py because this is going to be loaded in by C++, right? Now, within this Python module, you will put your code down in there. So, so this is Python code now. So C++ will be able to use these functions while it's executing, you know, any compute that is present in C++. So that's the cool part. Okay, so over here, what have we done? We've loaded in the Python module, right? And using these three lines over here, right? So we want to release the reference. So this is C++. We have to be careful with how we deal with our pointers, and we don't want them hanging over there, right? So, but at the end of this bit over here, we've loaded in the Python module. So the functions in the module are available to us for use, okay? Now, the functions are available, but we have to load them in. Okay, so in the sense that we can again use a Py object over here. And now instead of doing like an import, because we already imported the module, we have to, from the P module, import these functions. So again, so there are two functions that we're interested in, the collection function and the analysis function, right? Now these strings have to match the strings of the functions that you put in here. So for example, there is a collection function over here, right? That will be loaded in by C++. C++ can now call this. And there is an analysis function. Okay, we'll go into what these are doing as we call them in our C++ code. Please let me know if anybody has any questions. I'll be happy to.
Excuse me, Romit.
Yes.
Is there a place in the code where you instantiate the Py object, the object?
That's what's happening here. So it's instantiation and definition at the same time. So.
Okay, got it.
Yeah. So, okay. So, all right. So we are okay for now. What have we done? We've initialized Python from C. We have loaded in a Python module, and now we have loaded in the Python functions. So that's what we've done so far, okay? Now we are going to do some C++ stuff because we have to, at the end of the day, solve for the Burgers equation, this compute in C++, right? And so this is classic, I'm going to initialize a double precision array with my initial conditions, for example, and then I'm going to just solve for this, right? So initialize, let's take a look at the initialize function. This is a purely C++ function, okay? So there is a initialize function that returns nothing, that basically initializes my one-dimensional field with a sinusoid, okay? So I have an image that will tell you what I'm talking about. Oh, Bethany, did we get rid of the images?
Okay, if you click on the hands-on.md.
Ah, I see. Okay, excellent. So for example, this is what we are going to be solving for today, right? So initially you have this blue curve over here, that's a sine wave. And the Burgers equation basically is an advective diffusive equation, but our diffusion is very low. Again, this is some physics, but just to give you an intuition for what is happening, this wave gets advected. So, you know, it moves from the left to the right and from the right to the left when the solution is negative, and then it gets shocked in the middle, okay? So we want to simulate this. Or we want to simulate this in C++ and send this data to Python to do some reduced order modeling or some machine learning, okay? All right, so where were we? Okay, so we initialize a sine wave over here, nothing very fancy, right? We also initialize another dummy variable because we have to update this using like a classical finite difference method. So that's required. And we add a +2 over here because the array needs some ghost points on either side to implement our finite difference tensor. Don't worry about this detail, right? This is just memory to hold our solution in C++. Some standard initializations over here to check for how much time we are needing to solve this problem, right? So this is this guy. And then within this, this function, which is our time integrator, we will update our solution using C++. So let's go to the update solution. So over here, we have a very simple, you can see the explanation over here, right? We have a very simple update of this partial differential equation. Not going to go into the details over here, but this is something called an FTCS update. So forward time central space type of update. And at the end of the update, we want to make sure that the dummy array that we kept for recording the previous time step is copied or is overwritten by the updated solution. So again, nothing super difficult over here. This is a trivial example for the C++ compute. Now here's the interesting part. Now we want to send this solution to Python, okay? So you could have an if statement over here to send the solution to Python at every 10th time step, for example. But since this is a small problem, you can send it at each time step, right? So that's application specific. So now let's look at this function over here, collect data. How are we sending data to Python, okay? So I heard the beginnings of a question. I heard wrong, okay. So this collect data function, it basically grabs the solution from C++, right? That's what's coming into the function. And then it uses a numpy array data type, okay? It copies that solution into a numpy array data type, right? And then sends this to Python. That's what's happening. So if you remember, let me now open up my collection function example, my Python script. So we were in ML module, or sorry, Python module. And this is what the collection function looks like. Okay, so we have an input array. This input array has to be numpy. You can't send in any arbitrary thing over here, right? Because we are doing numpy operations on that array. So we have to first convert it into a numpy array type from the double precision type that was there in C. And that's what's happening over here. We will first initialize a numpy. So this statement over here is initializing a numpy array with a certain dimension, right? Nx plus 2. Nx plus 2 again is the dimension of our original array, right? And we'll get back to this statement in a while, but basically now okay, sorry. So this was this data type numpy intp is telling us how many points are there in our array, or what is the length of our array. And this array 1D is the numpy data type that is constructed using this information over here, and you give it the type information. So we want to use a numpy float 64, right? And then we want to copy over from U. Okay, so we copy over from U to array 1D. Array 1D is now something that Python can work on, right? And before sending it willy-nilly into Python, we want to put it into an argument tuple. So one of the things that you should remember is, if you create something in C++, to send it into the Python module for use in a function or otherwise, or a class object, you would need to first convert it, you would need to first put it into a tuple, a pi tuple, okay? And then you can send the pi tuple across. So that's what's happening over here. So there's a pi tuple. We only have one argument to send. So that's why there is just one over here, because this guy only takes one input, right? And we will just set the first member of this tuple to be our numpy array, okay? So that's p-args over here. We'll have another example where we'll have p-args with 2 items in it, okay? And then we send it across, well, we don't send it across, we call the function, okay? So we do a call object over here. So this is going to run the collection function from C++ while using p-args as the argument. And the argument was array 1D, okay? And from this, we get a return value. Over here, I'm not returning anything. So this p value is essentially a null pointer, but we still release the reference, okay? And that was how we collected data. So now what is happening? Where is this data that is collected being stored? Now this will start making sense to you in the sense of how robust this is for an arbitrary simulation plus ML interface. If you look at the data, if you look at where this data is being sent, so what was happening within this collection function, you were sending over this one-dimensional array, but it was being stored as columns of this two-dimensional data array, which was actually initialized over here when you loaded in the module. So that's you. So you can have like some data sitting in global memory that you can that's global in nature that you can actually overwrite, right? So that's really cool. So from C++, I'm overwriting this guy that was initialized by Python. And at the end of the day, the goal is to then do some learning on this array that you have over here, okay? So I've added a comment over here. You need to make sure that the dimensions of this array kind of match the dimensions of your C++ problem. For this trivial example, this is not difficult. 2001 is the number of times this collection will be called. So there'll be 2001 snapshots of this one-dimensional field that are being sent in. And 258 is nothing but nx plus 2. Okay, so that's how it's being saved over here. All right, so data collection is done. Now let's say we've finished running our solution. We have populated this entire data array over here. We want to go down and start doing some ML on that data array, right? So firstly, we are done with collection function, so we can release the reference to that particular pi object, okay? And we can output some information related to how long it took. So I'd encourage you in your free time to use the CPU time things to profile where you're spending some time in, for example, the numpy casting or the exchange of information and the overwriting. This is stuff that we are researching on our end, by the way, for larger problems to see where there might be some hotspots in pulling off this type of project. Okay. All right, now we are ready to analyze the data, right? This is the fun part. So this data has been saved. You see in the analyze data function, which is down over here. Again, we will have to use the pi object that we had instantiated and declared earlier or defined earlier in the code, which I'll remind you was here. So we had loaded in the analysis function, okay? And what we will do is we will actually just call the analysis function without any argument. Okay, because the analysis function, again, let's look at it, does not require any input. So I'm just sending in a null pointer here. I'm not using a pargs anymore. So this is a null pointer, so that makes life easy for us. But we can use Python to actually access this global array, which was overwritten by our collection function. So just setting a global over here is good enough for us to access this information. Okay. So and here, this line, we just call the analysis function and we get a return value. Okay. Now we're going to do a lot of cool things in the analysis function. Okay. So the first thing we're going to do is we're going to save the flow field or the solution field over time. And when you run this, it should run successfully. And actually, let me see if I can show you it should, it should overwrite and replicate this flow field identically. Okay, so that's the purpose of this section. Okay, so this is just basic Python matplotlib. So now from C++, you're able to run a matplotlib visualization. That's valuable as well. Now think of how much you can let your imagination run with this, right? You can store data using HDF5 over here without, you can just have an import H5 over here and you can store data using H5. Or you can use netcdf4. You can do so many things in Python because now your data is in Python already. So it's very easy to write code, right? What's next? So now with this data array, I use numpy now from within Python to perform an SVD. It's as easy as just one line over here. Now I haven't ever had to use any code in C++ to perform an SVD, fortunately. If there are people in the audience, you can try to compare this to how difficult it might have been to code up the SVD in C++ itself. But this is definitely something I prefer, okay? And then you can also, for example, make a second set of plots, which actually plots the SVD eigenvectors. So the U, S, and V that you get over here, you can make plots of, for example, the right singular vectors, and we will plot them like these. These are orthogonal. So they are basically kind of telling you about the flow field information when you plot them over the physical domain. So you see more oscillations near the discontinuity, because near the discontinuity, you do not have any frequency, you do not have enough frequency information to capture the entire field. Okay. Okay. So, and then you can even save your data in NumPy format, in .npy format. Okay, so you don't have to worry about sending it to C++ and then saving it in, I don't know, binary or text or something. Over here, it makes life easy for us to just save it in NumPy if you want to reuse Python in the future for some more analysis. Okay. What we will do after here is something very basic. What we will do is use TensorFlow, the Python API of TensorFlow, to actually train like a time series forecasting problem. Okay, so what we do is we actually construct a reduced representation of our flow field by multiplying these eigenvectors with the data itself. So the data, I'll remind you, was 2000 by 258, for example. So what we have now is a this V data set is this V0 to 3, and this colon is 3, 258, because it's plotted over the domain. And then what we end up with is a time series that is 3-dimensional in nature. And
Hi, Romit.
Yes.
So did you do this LSTM after your simulation is done? Or
yes. So I'll remind you, when are we calling this analysis function? This analysis function is being called after my simulation is done. So I'm training this LSTM after my simulation is finished. Right? But you could, for example, call TensorFlow in the middle if you think that, oh, I can start using some of this data for training already. Does that make sense?
Yeah, that's cool. Okay. Thank you.
Mm-hmm. So, all right, so I've reduced the dimension. So the SVD can be used for projecting your data onto a low dimensional subspace. You can use the low dimensional subspace to, you can interpret it to be a time series. You don't have to interpret it. It is a time series. You can use the time series, and then you can train an LSTM on it. So now what do we do? So now it's basic Python. You don't have to worry about C++ anymore. So you can, for example, you can import a standard LSTM, okay, which I have defined in another module. So let's go in there. We'll be running all this, so don't worry. So over here, there is another ML module that now it's just basic Python. So over here, I have all these standard imports that that you might be using when you fit an LSTM. I've built an LSTM model. I didn't use the vanilla LSTM that is available in TensorFlow Keras. I decided to use my own subclass of a model. This is just because I had it for another project and I just copied it over, and I'm going to, so this is entirely Python. Okay, so we don't have to worry about what is happening over here, except that an LSTM is being trained. It's a type of neural network for time series data. It's being saved, restored, etc. All of this is being done in Python, but it's being called from C via the analysis function over here. Okay, so I train my LSTM using, this ML model, and then I call the train model, and then I do some inference on some testing data that I held out. My model inference again is it just restores the model again in Python from the disk, from the checkpoint. It does some transformations, it does some reshaping, and then it just makes a prediction using the LSTM. Okay, and that's what's happening. All of this rather large code is wrapped into just one C++ function call. Okay, and at any moment in time, you could have, for example, had an if statement and returned some data to C++ if required. So I haven't really been very very steadfast when it comes to doing error checking and things like that. So I'd encourage you to do the same, but this mini app kind of gets the idea across. Okay, so so now we are ready to essentially run this code. Does everybody understand what exactly is happening over here and what we are trying to do? Does anybody have any questions before we go into the hands-on?
So, hi Romit, I'm wondering, why didn't you call C++ code within Python? Was there any drawback?
No, the assumption is that this compute that I'm showing you, right? This is like 3 lines. In this case, it's 3 lines. So you could have done this entire thing in Python if you wanted, right? But now let's say that this is something like NEC 5000 or, OpenFOAM, where your C++ code is millions of lines, right?
Yeah.
You don't have the luxury to rewrite the entire thing. I mean, you could call the C++ code in Python, and we have considered it, but we found it way easier to just embed this sort of a little bit of like a small class object within a larger code that calls Python for us. So
suppose, what would you recommend? Like, if I would like to call a flow code like OpenFOAM, write code within Python or in OpenFOAM?
I'd recommend you just use the repository we've put out. That'd be good for both you and me. But but we've essentially done the same thing. We've used OpenFOAM, and within OpenFOAM we have made our own say. So OpenFOAM allows you to write your own solver, for example, right? It allows you to write your own model, your own boundary conditions, stuff like that. So you can just make a new one, but within that you can call Python to do some computation for you. So for example, the paper that Bethany referred to, in that we had a turbulence model where we just copied an existing turbulence model, but in the copied version of the model, we switched it off, and we just called a Python command. So it was easier than figuring out how to call open from Python in an efficient manner. So yeah, but my experience is asymmetric. So in one direction, we've done a lot of digging, C++ to Python. In the other direction, we've just brainstormed it. We haven't really done anything. So there might be a competitive way to do it by, keeping the main function in Python as well. That's definitely there. So
thank you.
Yeah, sure. Okay,
Romit,
so yes.
Could you clarify what exactly you're training? By that I mean, what exactly are the features and the outputs of your training
Oh,
model?
it's a very trivial type of example. So over here, once you do this matrix multiplication, right, this time series that you get will be will essentially be 2000 by 3. So we take the eigenvectors coming from the right eigenvectors coming from the SVD, right, and we project. So those are an orthonormal basis, right? So we project the flow field or the actual solution onto those eigenvectors, and we get a we can represent the flow field using coefficients of those 3 eigenvectors. Okay, so it's something called the PODLM approach. So you construct a proper orthogonal decomposition of your flow field. You get these modes. These are kind of similar to the Fourier modes, and we project our solution onto those modes, and we get coefficients for each coefficient for each frequency. So in Fourier, it would be frequency. Over here, it's a eigenvector, and we can evolve the coefficients in time rather than actually evolve the entire solution, because using the 3 coefficients, we can reconstruct the flow field at any time. Does that make sense?
Yeah, so basically you're training the model to output better coefficients, if I'm right.
Hopefully the right coefficients. As you'll see in this particular example, it doesn't do a very good job, but it gets the idea across. So it's basically, yeah, you could, for example, even bypass this particular call with a convolutional autoencoder based forecasting, right? You could give it all 256 data points, right? Put it into like a 1D convolutional autoencoder and ask it to predict the next 256 points on our solution field. So it's like solution input, solution output. You could do that. We just wanted to simplify the problem by projecting it onto a lower dimensional sort of subspace. So now it's only 3-dimensional, and we can use an LSTM. So that was the idea.
So it's
okay, and so in the loss function, you're basically minimizing the difference between the actual flow field and the reconstructed flow field, right?
Not the flow fields, in this case, the coefficients itself, because it's a linear operation between coefficient and flow field. So it's the same thing.
Okay, got it.
That's right.
Thanks.
As the big picture, the big picture is being able to predict the flow field.
Yes.
But the it's set up as actually predicting the PCA coefficient.
Yeah, we just predict the PCA coefficients initially, and then we can reconstruct later, which we haven't done over here, but that's good homework, good suggestions. Okay, so and that's what the inference is doing over here. So we're training, and then we're doing the inference. Okay, so at this point, let's before we start doing some hands-on, let's just go through how we want to build this app. Okay, so let me go back to. So this is our base camp. So over here, we now define the app. We know how our working directory should look like. It should have my 2 Python modules, ML module and Python module. Was there another module? No, it was just these 2 modules that we were going to use. And all of this other thing is just, like previous outputs by the code itself when we were testing it. But we want to build this now, and we want to build this using CMake. So let's look at a CMake lists. Okay. Oops, sorry about that. Right. So the way we'd want to build this app is that it should obviously be able to call these bindings so that you can talk to Python and exchange data with it. And in order to do that, you actually need to make sure that you have libpython.so in your path, right? So you need to make sure that both the numpy header files and the Python header files and the Python libraries are available to you at both compile time and runtime. So and that CMake makes that really easy for us to do. So for example, you will have these 2 lines over here, which are called include directory. So these are any header files that we will need to have access to the C API functionality of Python. So in Theta, I have taken advantage of these optimized packages that the data science team works really hard on providing for us. So we just grab this directly. And also, for example, all of these packages also have numpy on them, because for data science, you generally always need numpy. So the numpy core include gives us access to, there's a numpy core api.h file in there that helps us use the numpy data types and the numpy API, right? So this is just telling us app.cpp is the file which we need to compile, and this command over here, find library, is actually telling us that the libpython 3.6m.so that we need during runtime is available over here as well. Okay, so you won't have to change this if, for example, you want to run this problem with your, with your toy example. But for example, if your C++ code, needs to be compiled with Python, then you will have to look at the compilation strategy that you've used for your C++, your legacy code, and then find a way to include this information, these guys over here and this guy over here, so that when you then execute your C++ code, you don't have to worry about not finding Python and not being able to use these bindings. So we have obviously accomplished this using CMake over here, but in OpenFOAM, as someone was asking, OpenFOAM does not use CMake, it uses WMake, which is a derivative of make. And in WMake, we had to basically point OpenFOAM to these directories, and then OpenFOAM was able to use it. So this is just basics of compiling and linking, which if you're a C++ user, you're probably familiar with. Okay, so that's the CMake lists that we need. And let's also look at some of the submit scripts. So we will be going through these examples in a while, but what we will essentially need is to, when we run this interactively, we will need to append the path, right? We need to append the location of those data science optimized libraries to the LD library path and the Python path, and this is also set up over here. You don't need to fiddle with this. And then finally, we just run CMake. That's it, pretty much. And then we are able to run some examples. So I will start with theta KNL, which is slightly slower. And then we can move on to theta GPU, which is alarmingly fast, and that makes me happy as well. So, okay, so shall we get started? I can pause here for a few minutes to give you a break. We have 3 minutes maybe for a break, some questions, refilling your coffee, etc. Does that sound like a good idea?